Hey guys, it's Murat Duman here. In the first video I talked about the introduction part of differential equations, and in this video I will talk about the first order differential equations more, and we will see the solutions for the more general form of first order differential equations. In this chapter there are 9 subtopics as you see, and let's start with the linear equations with variable coefficients. In the previous chapter, we dealt with the simplest form of the first order differential equations, which is dy over dt is equal to ay plus b, where a and b are constants. And it is the simplest form. In this chapter, we will deal with a more general form of the first order differential equations, and it is dy over dt plus pt times y is equal to gt. More general form of the first order differential equations, and as you see, a and b are not constants anymore. I will explain the reason why later, but for now let's multiply both sides with a function mu of t, and we get mu of t times dy over dt plus p of t mu of t times y is equal to mu of t g of t, and let's call our first equation. And what we did here is by multiplying both sides with a function mu of t. And at this point, let's remember the product rule for derivatives. And let y of t and mu of t be our two functions for this operation. The derivative of first function y of t times mu of t plus derivative of the second function times the first function. And as you see here, this part is already exists in our first equation here. And let's write it down. Already exist in the left hand side of the equation 1. So if this remaining part is equal to this part, then we can use the product rule for the left hand side of the equation 1. And let's write it down. If this part is equal to p of t times mu of t times y, then we can write the left hand side of the equation 1 by using product rule. And maybe here, instead of y, I should have written y of t, but I already know y is dependent variable and it is already dependent on t. And let's continue from here and equate this part and this part. And by integrating both sides, we get ln in absolute value mu of t is equal to integral p of t dt plus c. And for the sake of simplicity, we will choose 0 for c. And from here, mu of t is equal to e to the integral p of t dt. If we choose mu of t in this form, then we can use the product rule for our first order differential equation. And by using product rule, we can easily solve our first order differential equation as given in the form of the equation 1. And let's turn back to equation 1. By using the product rule for the left hand side of the equation 1, we can write the equation 1 as d over dt mu of t times y of t is equal to mu of t times g of t. And by integrating both sides, mu of t times y of t is equal to integral mu of t times g of t dt plus the constant c. And from here, y of t is equal to integral mu of t g of t dt plus the constant c over mu of t. And this is the solution that we look for y of t. And let's solve some problems. Our differential equation is given in this form, and we are asked to solve the initial value problem and find the critical value for a0, which is the value of which the transition from one type of behavior to another occurs. And we are trying to make the coefficient of the highest order term 1. Since this is a first order differential equation, we will try to make the coefficient in front of y prime 1. So we will divide both sides by 2. So y prime minus y over 2 is equal to 1/2 e to the t over 3. And our multiplication term is e to the minus 1 over 2, as you see from here. E to the minus t over 2. And multiplying both sides by this term, we will get by integrating both sides, and by using the given condition, which is y0 is equal to a is equal to minus 3 plus c, and from here c is equal to a plus 3. And from here our solution is if this term is a positive term, then this term will be added as a plus term. Otherwise, this term will be added as a negative term. So, by equating a0 plus 3 to 0, we will get minus 3 for a0, which is the critical value. Our second problem, we are asked to construct a first order differential equation whose solutions are asymptotic to the line y is equal to 3 minus 3 as t goes to infinity. And then we are asked to solve this equation and confirm that this solution has this specified property. All the first order differential equations that we have seen up to now are close to this form. Y prime plus a times y is equal to something, and let's say original. And for the sake of simplicity, let's choose a as constant. And this a is related to the integrating factor, because we define integrating factor as e to the integral a times dt, and the integral of an exponential function is still an exponential function. By choosing a proper value for a due to its sign, we can adjust whether our function will exponentially rise or decay in time. So, in this question, a is related to the adjustment of our function to asymptotically getting closer to the line y is equal to 3 minus 3. So our integrating factor is equal to e to the at. By using this integrating factor, we get y prime e to the at plus e to the at times y is equal to original part times e to the at. By using product rule for derivatives for the left hand side of our equation, we get d over dt y times e to the at is equal to original part times e to the at. And from here, y e to the at is equal to integral original part times e to the at dt plus the integration constant c. And let's call this integral capital A. So y times e to the at is equal to capital A plus c. From here, y is equal to a times e to the minus at plus c times e to the minus at. This term is related to asymptotically getting closer to the line y is equal to 3 minus t. So from here we understand that a is bigger than 0. So this part will attenuate in time, and this part is equal to 3 minus t. As we remember, capital A is equal to the integral of original part times e to the at dt. As we see from here, capital A times e to the minus at is equal to 3 minus t. So this integral is equal to capital A, and dividing capital A by e to the at, we get 3 minus t. By differentiating both sides, we get the original part times e to the at is equal to d over dt times 3 minus t times e to the at, and it's equal to e to the at times 3a minus at minus 1. So original part is equal to 3a minus at minus 1. If we turn back to the beginning, y prime plus ay is equal to the original part. So y prime plus ay is equal to 3a minus at minus 1. This is the differential equation that we asked for. Let's continue with the separable equations. If our differential equation is separable, in other words, if our differential equation can be written in this form, then basically by using integration we can get the solution. Let's continue with some problems. In our first problem, our differential equation is given in this form and we are asked to find the solution. First of all, let's remember the fact that 1 over cosine square x can be written as 1 plus tangent square x. So we can write our differential equation as y prime times 1 over cosine square 2y is equal to cosine square x. And we can write this term as y prime times 1 plus tangent square 2y is equal to cosine square x. If you write the left hand side in the open form, we get dy over dx plus tangent square 2y times dy over dx is equal to cosine square x. And from here, dy times 1 plus tangent square 2y is equal to cosine square x dx. As we see from here, we wrote our differential equation in the separable form. So, by integrating both sides, we get 2 tangent 2y minus 2x minus sine 2x is equal to c. And since tangent 2y is equal to sine 2y over cosine 2y, we must keep in mind that cosine 2y must not equal to be 0. In order to keep our differential equation definite, let's write it down. If cosine 2y must not equal to 0, or y is equal to plus or minus 2n plus 1 times pi over 4, and it's for integer n. Our second differential equation is given in this form, and again we are asked to find the solution. We can write our differential equation in this form: dy over 1 minus y squared over 1 half is equal to dx over x. And here we will change our variable as y is equal to sine a. And from here, dy is equal to cosine a times dA. By using this information, we get dA is equal to dx over x. And by integrating both sides, a is equal to ln absolute value of x plus c. And from here, we know that a is equal to arc sine y. So, we use this information here. Arc sine y is equal to ln x plus c. And finally we get y is equal to sine ln x plus c. And we know that ln 0 is equal to minus infinity, and in order to keep our solution to be definite, x shouldn't be equal to 0. And this is our solution. In the third question, differential equation is given in this form with an initial condition. We are asked to find the solution and determine the interval in which the solution is defined. 1 plus 2y dy is equal to 2x dx. And by integrating both sides, we get y plus y squared is equal to x squared plus constant c. And by using the initial condition, y2 is equal to 0, we get c as minus 4. So, by using this c value, we can write this equation: y squared plus y is equal to x squared minus 4. In order to write the left hand side as a square function of y, we add 1 over 4 to both sides. So we can write the left hand side of equation as y plus 1 half squared is equal to x squared minus 15 over 4. So y is equal to minus half plus or minus square root of x squared minus 15 over 4. If we use the initial condition, which is y2 is equal to 0 here, we will see that we can only use the plus sign here, not minus. So let's correct the solution. Y is equal to minus half plus square root of x squared minus 15 over 4. And this value must be bigger than 0, so we must add this to the solution. X squared is bigger than 15 over 4. And this is the solution of our problem. In this question, our differential equation is given in this form with an initial condition. We are asked to find the solution and plot the graph of the solution and determine the interval in which the solution is defined. We can write our differential equation in this form: x dx is equal to minus y e to the minus x dy, and if we integrate both sides we get integral x e to the x dx is equal to integral minus y dy. And here, if we use partial integration methods, we get x e to the x minus e to the x is equal to minus y squared over 2 plus c. If we write this equation in a more tidy way, we get 2e to the x 1 minus x plus c is equal to y squared, and from here y is equal to plus or minus square root of 2e to the x 1 minus x plus c, and here we will use the initial condition, which is y0 is equal to 1, and from here we get c is equal to minus 1. So in order to satisfy this initial condition, the sign in front of the square root must be plus. So y is equal to square root of 2e to the x 1 minus x minus 1. If we plot this solution using MATLAB, we get this graph. Since our solution contains square root term, the value inside the square root must be positive in order to keep our solution real. And as it is seen from the graph, for the x values that are between minus 1.68 and 0.77, y is bigger than 0. So this solution is valid for the x values that are between minus 1.68 and 0.77. And this is our solution. Let's start modeling with first order equations. This is one of the most important parts in this book, because the main skill that we are trying to achieve is modeling a given problem using differential equations. The basic idea is the rate of change of any given quantity, let's say dq over dt, is equal to the rate at which the quantity is increasing minus the rate at which the quantity is decreasing. Let's write it down. Rate in minus rate out. The best way of understanding modeling with first order differential equations is modeling many questions by using differential equations, and that's what we are gonna do. Let's start with the first problem. In our first problem, a body of constant mass is projected away from the Earth in a direction perpendicular to the Earth's surface with an initial velocity v0. There is no air friction, but Earth's gravitational field. We are asked to find an expression for the velocity during the motion, to find the initial velocity that is required to lift the body to a given maximum altitude alpha above the surface of the Earth, to find the smallest initial velocity for which the body will not return to the Earth. It's called escape velocity. This is the Earth and its radius r. This is the positive x direction. But the gravitational field is towards to the Earth. Let's say F gravity. Gravitational force is inversely proportional to the square of the distance. F gravity is inversely proportional to the some constant over distance square. Gravitational force is calculated according to the center of the Earth, so the distance here is r plus x. Gravitational force is the function of the distance, so F gravity, let's say omega x, is equal to k over x plus r square. And there will be a minus here because the gravitational force is towards to the center of the earth, which is in the minus x direction. When we are on the surface of the earth, where x is equal to 0, F gravity is basically equal to mg, where x is equal to 0. So omega 0 is equal to minus k over x plus r square, which is equal to mg. And from here, k is equal to mg r square. So omega x is equal to minus mg r square over r plus x square. Since there are no other forces like friction, air friction, force is equal to mass times acceleration, which is equal to mass times dv over dt, and it is equal to minus mg r square over r plus x square. There are many variables in this equation: speed, time, and x, which is the distance. So we will eliminate one of these variables using the chain rule. dv over dt is equal to dv over dx times dx over dt. dx over dt is equal to v, so dv over dt is equal to dv over dx times v. Let's use what we have found here. M times dv over dt is equal to m times dv over dx times v, and it is equal to minus mg r square over r plus x square. So dv times v is equal to minus g r square dx over r plus x square. If we integrate both sides and solve this basic integration, we get v square over 2 is equal to gr square over r plus x plus c. And in order to find the constant c, we will use the given initial value here, which is the speed value where x is equal to 0. It is v0. And let's use this initial value in this equation. So we will get v0 square over 2 is equal to gr square over r plus x, but x is 0 here, plus c. So c is equal to v0 square over 2 minus gr. Let's use the value of c in this equation again. So v square over 2 is equal to gr square over r plus x plus v0 square over 2 minus gr. And from here, v is equal to plus or minus square root of v0 square minus 2gr plus 2gr square over r plus x. Note that velocity is the function of distance here, not time. And the plus sign must be chosen if the object is moving away from the earth, and the negative sign must be chosen if the object is getting closer to the earth. And this was part A. Let's continue with the part B. And in the part B, we are asked to find the initial velocity that is required to lift the body to a given maximum altitude alpha. At the maximum altitude, the object is changing its state from moving away from the earth to the getting closer to the earth. So at the maximum altitude, v is equal to 0 and x is equal to alpha, as it is given in the beginning of the problem. So let's use these values in the equation that we have found for the velocity. So 0 is equal to v0 square minus 2gr plus 2gr square over r plus alpha. And from here, alpha is equal to V0 square R over 2GR minus V0 square. And solving this equation for V0, we get V0 is equal to square root of 2GR alpha over R plus alpha. And in part C, we are asked to find the escape velocity. Let's call it V sub e. The escape velocity V sub e can be found by letting alpha goes to infinity. So let's write it down. Escape velocity can be found by letting alpha goes to infinity. If we put infinity for alpha here, we get V sub e is equal to square root of 2GR. And this is the end of this problem. In the second question, a tank contains 200 liters of dye with a concentration of 1 grams per liter. The tank is rinsed with fresh water flowing in at a rate of 2 liters per minute. This solution is flowing out of the same rate. We are asked to find the time that will elapse before the concentration of dye in the tank reaches 1% of its original value. Let's say the mass of dye in the tank is demonstrated by Q. So the rate of change of dye per unit time is demonstrated by dQ over dt. The unit of dQ over dt is given as grams per minute. Q is the mass of dye. And let's remember the general formula for differential equations. dQ over dt is equal to rate in minus rate out. The tank contains 200 liters of dye with a concentration of 1 gram per liter. So the initial amount of dye in the tank is given by 200 liters times 1 grams per liter, and it's equal to 200 grams. So Q0 is equal to 200 grams. Since the tank is rinsed with fresh water and no flow of dye into the tank after T is equal to 0, and 2 liters of the solution, which is the 1% of the solution in the tank, flowing out of the tank, so dQ over dt is equal to minus Q, which is the current amount of dye in the tank, over 100. From here, dQ over Q is equal to minus dt over 100. If we integrate both sides, we get ln Q is equal to minus t over 100 plus c. And from here, Q is equal to e to the minus t over 100 times c. We will find the constant c from the initial condition, which is Q0 is equal to 200 grams. So Q0, which is 200 grams, is equal to e to the minus 0 over 100, which is 1 times c. So c is equal to 200. And let's put this number in this equation. Q is equal to e to the minus t over 100 times 200. In the question, we are asked to find the time that will elapse before the concentration of dye in the tank reaches 1% of its original value. 1% of 200 grams is equal to 2 grams. So 2 is equal to e to the minus t over 100 times 200. And from here, 0.01 is equal to e to the minus t over 100, and ln 0.01 is equal to minus t over 100. And from here, t is equal to minus ln 0.01 times 100, and t is equal to 460.5 minutes. In this problem, we are given a liquid problem. The tank in the problem has 500 gallons capacity. And initially it contains 200 gallons of water with 100 pounds of salt in the solution. Water containing 1 pound of salt per gallon is entering at a rate of 3 gallons per minute, and the mixture is flowing out of the tank at a rate of 2 gallons per minute. We are asked to find the differential equation which gives the amount of salt in the tank at any time prior to the instant when the solution begins to overflow. First of all, we need to determine how much time we have before the overflow, and the differential equation will be valid in that time interval. Water is entering at a rate of 3 gallons per minute, and the mixture is flowing out of the tank at a rate of 2 gallons per minute. So each minute the volume of the solution will increase in 1 gallon. Since there is already 200 gallons of water in the tank, we have 300 gallons of space remaining at the beginning. It means before the overflow we have 300 minutes. So T is smaller than 300 minutes. Our variable Q here is the current amount of salt. And our differential equation will be in this form: dq over dt is equal to flow in minus flow out. 1 pound of salt per gallon is entering at a rate of 3 gallons per minute. So the entering salt to the tank is 3 pounds per minute. So this part is 3. What is the mixture that is flowing out of the tank? The current amount of salt is Q, and what is the ratio of Q that is flowing out of the tank? The mixture that is flowing out of the tank is 2 gallons, and the total amount of mixture is 200 plus T. Because each minute the increase in solution is 1 gallon. So our differential equation is dq over dt is equal to 3 minus 2 over 200 plus T times Q. This is the differential equation that we look for. Fourth question: I borrowed $100,000 at an interest rate of 9%. I expect to make payments at a monthly rate of this function, where T is the number of months since the loan was made. In A, when will the loan be fully paid? In B, with the same payment schedule, how large a loan could be paid off in exactly 20 years? Q is the current debt, and our differential equation is in the form of dq over dt is equal to rate in minus rate out. Rate in is current debt times the interest rate, which is 9%, and since we have monthly payment schedule, we should find the monthly interest rate, so we will divide 9% to 12. And rate out is the monthly rate, which is 800 times 1 plus T over 120. So dq over dt minus 0.0075 Q is equal to minus 800 1 plus T over 120. By using integrating factor, we will get this equation. After a few steps of simple calculation, we will get in order to find this constant C, we will use the initial condition, which is Q0 is equal to 100,000 and it is equal to, and from here C is equal to minus 125,186, and we will use this constant C in our equation, so Q is equal to and this is the function that we look for. And in part A, we are asked to find when the loan be fully paid. So, in order to find the point where the loan or debt is equal to 0, we will plot this function by using MATLAB. And as it is seen from the graph, at the end of 135th month, the loan will be fully paid. And this is the part A. And in part B, with the same payment schedule, we are asked to find how large a loan could be paid off in exactly 20 years. Since the initial condition, which is the loan at time 0, changed, we will calculate the new constant C, because we are calculating C by using the initial condition. Let's write down the equation for Q. After 20 years, which is 240 months, the loan will be 0. So, and from here C is equal to minus 72,491. So by using this constant C, we will calculate the initial loan, which is Q0. Q0 is equal to minus 72,491, which is equal to 152,695. The population of mosquitoes in a swamp increases at a rate proportional to the current population. In the absence of other factors such as predators or the lack of food or space, the population doubles each week. Initially, there are 200,000 mosquitoes. Predators eat 20,000 mosquitoes per day. Determine the population of mosquitoes in the area at any time. Let's write the general form of our differential equation, which is dq over dt is equal to rate in minus rate out. First of all, we will think about the situation in which there is no predators around, so rate out will be equal to 0. And as it is said in the question, the population of mosquitoes in a swamp increases at a rate proportional to the current population, so rate in is equal to K times Q. And Q is the current population here. So dq over dt is equal to K times Q, and dq over Q is equal to K times dt. And integrating both sides, we will get ln Q is equal to K times T plus C. And from here, Q is equal to e to the kt times C. We will get C from the initial conditions, and as it is said in the question, initially there are 200,000 mosquitoes, so Q0 is equal to 200,000, which is C. So our equation is Q is equal to 200,000 times e to the kt. As it is said in the question, in the absence of other factors, the population doubles each week. So after 1 week, the population of mosquitoes will be equal to 400,000. So Q1 is equal to 400,000 is equal to 200,000 times e to the k. T is equal to 1 here, so I will not write it. From here, k is equal to ln2. Now we will consider the situation which there are predators around, so this time rate out will not be equal to 0. Predators kill 20,000 mosquitoes per day, but we will not use this value since we calculated the constant k value by using the weekly increase in population. So our rate out will be 20,000 times 7 and it will be equal to 140,000. So dq over dt is equal to k times q minus 140,000. By using the integration factor, we will get this equation. Where k is equal to ln2. We will calculate the constant c value by using the initial condition. So c is equal to 200,000 minus 140,000 over ln2, and it's equal to minus 1977. So our solution for q is and this is the equation that we look for. And now we should specify the time in which this equation is valid, because after a certain time the mosquitoes in the swamp will get extinct. So the q value, which represents the population, will be equal to 0. So and from this equation the final value will be found as 6.674 weeks, and here t is smaller than 6.674. Sixth question. A certain population has a growth rate that varies with time, and this population satisfies this differential equation. Part A. If y0 is equal to 1, we are asked to find the time tau at which the population has doubled. We'll choose other initial conditions and determine whether the doubling time tau depends on the initial population. Part B. We'll ask to suppose that the growth rate is t over 10 and determine the doubling time tau. Part C. We are asked to suppose that sin t in the differential equation is replaced by sin 2 pi t. What effect does this have on the doubling time tau? Part D. We'll ask to plot the solutions obtained in parts A, B, and C on a single set of axes. Let's first start to solve the differential equation. By integrating both sides, we will get and in order to find the constant c, we will use the initial condition, which is y0 is equal to 1. And from this equation we will get the constant c as e to the minus 0.2. And we will put this constant c in our equation and we will get the solution as in part A, we are asked to find the time tau at which the population has doubled. We know y0 is equal to 1. So, if tau is our doubling time, then y tau will be equal to 2. Let's use this in our equation. We will plot this function by using MATLAB and we will observe at which time instant our function will be equal to 2, and that instant will be our tau, which is the doubling time. As it is seen from this graph, our function reaches 2 when the time is equal to 2.97, so our tau is equal to 2.97. This was part A. And also in part A, we are asked to choose other initial conditions and determine whether the doubling time tau depends on the initial population. Now let's consider the situation which is given in this problem again. Our function was equal to y is equal to e to the 1 over 5 times 0.5 t minus cosine t times c. And we use initial condition to find the constant c. And c was equal to e to the point 2 and y is equal to since our initial population is 1, in order to find out the doubling time tau, we try to find out at which time instant tau the population is equal to 2. So y tau is equal to 2 and it must be equal to our function, which is e to the 0.2 plus 0.1 tau minus cosine tau over 5. And we use MATLAB in order to find out at which time instant tau this function is equal to 2, as it is seen from here. Now let us use another initial condition in order to see what changes. Our function is still same, y is equal to e to the 1 over 5 times 0.5 t minus cosine t times c, and this time let's take y0, the initial condition, is equal to 2, and this time the constant c is equal to 2 times e to the point 2. And let's reorganize our function by using this new constant c. Y is equal to e to the point 2 plus 0.1 t minus cosine t over 5 times 2. This time y0 is equal to 2, so y tau, the doubling time, is equal to 4. Now we will try to find out at which time instant tau our function is equal to 4. And our new function is as it is seen from here, two equations in order to find out the doubling time tau are same. So the doubling time tau doesn't depend on the initial population. Let's write it down. The doubling time tau doesn't depend on the initial population. This is the end of part A, and let's continue with the part B. And in part B, we are asked to suppose that the growth rate is 1 over 10 and determine the doubling time tau. This time our differential equation is relatively easy because our growth rate is just a constant. And from here the y over y is equal to 0.1 dt. And from here ln y is equal to 0.1 t plus c. And y is equal to e to the 0.1 t times c. And in order to find c, we use initial conditions. This is our initial condition and is equal to 1. So y0 is 1. So y tau will be equal to 2, which is equal to e to the 0.1 tau. And from here ln 2 is equal to 0.1 tau, and from here tau is equal to roughly equal to 6.93. And let's continue with part C. In part C, we are asked to suppose that sin t in the differential equation is replaced by sin 2 pi t. What effect does this have on the doubling time tau? As you remember, our first differential equation is dy over dt is equal to 0.5 plus sin t times y over 5. And our new differential equation is dy over dt is equal to 0.5 plus sine 2 pi t times y over 5. As you see, the frequency in our differential equation is changed now. Let's calculate our new doubling time tau. Dy over y is equal to 0.5 plus sine 2 pi t over 5 dt. And let's integrate both sides. ln y is equal to 0.1 t minus cosine 2 pi t over 10p plus c. And from here y is equal to e to the 0.1 t minus cosine 2 pi over 10 pi plus c. And in order to find the constant c, we will use the initial condition, which is y0 is equal to 1. And from here the constant c is found as 1 over 10 pi. Now our function is equal to e to the 0.1 t minus cosine 2 pi over 10 pi plus 1 over 10 pi. Our initial population is 1, and in order to find out our doubling time tau, we will look at which time instant tau our function is equal to 2. And by using MATLAB, we will try to find out at which time instant tau our function is equal to 2. As this seen from the graph, our function is equal to 2 when the time is equal to 6.39. So our doubling time tau is equal to 6.39. In part A, our doubling time tau was equal to 2.96, and now it's equal to 6.39. So the doubling time tau depends on the frequency in our differential equation. Let's continue with the part D. And in part D, we are asked to plot the solutions obtained in parts A, B, and C on a single set of axes. And by using MATLAB, let's do this. Now we clearly see all three functions that were found in part A, B, and C, and all three different doubling times due to changes in our differential equation. And here we clearly see the effect of change in frequency. Here the blue colored function is the solution of dy over dt is equal to 0.5 plus sine t times y over 5. And the green colored function is the solution of dy over dt is equal to y over 10. And the black colored function is the solution of dy over dt is equal to 0.5 plus sine 2 pi t over 5 times y. The growth rate here is replaced by its average value 1 over 10 here. But as you see, it seems like the green colored function has nothing to do with the blue colored function. And same situation is valid for the black colored function. As you see, the growth rate here is replaced by its average value here. But as you see, different from the other case, the black colored function seems like as it converges to the green colored function. Let's go one step further and choose sine 20 pi t this time. Here, the magenta colored function is the solution of dy over dt is equal to 0.5 plus sine 20 pi t over 5 times y. As you see, the magenta colored function is very close to the green colored function. So we can say that as we increase the frequency in our differential equation, we can replace the growth rate in our differential equation by its average value. Let's write it down. As we increase the frequency in our differential equation, we can replace the growth rate in our differential equation by its average value. It is the end of the problem. Since modeling problems by using differential equations is very important, for the next video I'll continue with solving problems on this topic. If you like this video, don't forget to subscribe. See you